In this lab, we are analyzing the physics of extreme sports with ropes by collecting data from a smaller model of a similar concept. The object of this lab is to create a model of the motion of a mass oscillating on a spring and compare it to a computational model created using predicted values. Once again, we will be using Newton's second law with the addition of the energy principle in order to analyze the physics behind this motion. As you can see in the video to the right, we will be analyzing the motion of the oscillating mass that is attached to a spring. Before we begin with the analysis, there are a few physics principles that will need to be introduced in order to understand the basic concept of oscillations in springs. Newton's second law states that the change in momentum is equal to the net force times the change in time. For this lab, we will be rearranging this formula in order to utilize basic formulas to find updates in position or velocity. The velocity update formula states that the change in velocity is equal to the net force times the change in time divided by the mass, while the position update formula states that the change in position is equal to the average velocity times the change in time. The forces in the system, which consists of the mass, the spring, and the earth, include the force of gravity and the spring force, as you can see in the slide. Moreover, there's another important concept known as the energy principle. The energy principle states that energy is neither created nor destroyed, but merely transferred from one type of energy to another. Because we know that there are no outside forces acting on the system, the change in total energy will be equal to zero, as there is no work from the surroundings. In this lab, the change in total energy will be equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. Kinetic energy is equal to 1/2 times the mass times the velocity squared. Gravitational potential energy is equal to the mass times the gravitational constant of the Earth times the height, and spring potential energy is equal to 1/2 times the spring constant times the amount of distance the spring is stretched or compressed squared. As you can see in the lab video, I used the pivot where the spring was attached as the origin and recorded the points from each frame of the video as the mass was oscillating to obtain the x and y position values over a certain amount of time. The observed values of this lab are that the hanging mass is 0.402 kilograms and the length of the spring is known to be 0.7 meters as given. The initial position of the mass was found to be negative 0.111 meters in the x direction and negative 0.636 meters in the y direction, while the initial velocity was known to be zero as the mass started from rest. In order to calculate the spring constant, I needed to find the period of one oscillation, so I looked at my graphs and looked at the time it took for two oscillations and divided it by 2 in order to get the time for one oscillation. Once I found the period, I rearranged the period formula and inputted the known values in order to find a spring constant of 6.874 newtons per meter. After finding the spring constant, I had to calculate the relaxed spring length by setting the magnitude of the force of gravity equal to the magnitude of the spring force. Then I rearranged the equation to solve for the relaxed spring length and inputted the known values, including the spring constant I had just solved for. After the calculations, I got a relaxed spring length of 0.1269 meters. In order to obtain a prediction of the computational model, I first readjusted the system's mass to be 0.402 kilograms and changed the initial position and initial velocity to be identical to the known values I had introduced in the slide before. Then, I changed the gravitational constant of the Earth to be 9.8 meters per second squared and changed the spring constant and the relaxed spring length to match the values I had calculated in the previous slides. Next, I changed L, which is the length of the spring, L hat, which is the direction of the spring, and S, which is the amount of distance the spring is stretched or compressed. Then I inputted the equations for this kinetic energy K, gravitational potential energy mu UG, and spring potential energy US that we had discussed in the physics principles. Then I added the 3 up to equal the total energy. In this loop, I defined the force of gravity, the spring force, and the total energy using the equations found in the slide for physics principles. I also inputted the velocity update formula and the position update formula, where ball.vel and ball.pos are located in the code. Then I wrote the same equations for L, L hat, and S, and wrote down the fitting equations for kinetic energy, gravitational potential energy, spring potential energy, and total energy. However, this time I also included the change in kinetic energy, the change in gravitational potential energy, the change in spring potential energy, and the change in total energy as well in order to plot these onto graphs. After running the code, I was able to retrieve an accurate model of the video that I analyzed. As you can see, the model portrays the oscillations and the total pass the mass took due to the oscillations. Moreover, we can also see that the change in energy versus time graph where the change in total energy is constant and zero throughout the oscillation. We can also analyze the change in position in the x-axis over time and the change in position in the y-axis over time in both our model and the experiment. As you can see, the two graphs are slightly off. However, this may be due to the fact that I had to hand plot the positions of the mass and tracker. In this lab, we can see that our models satisfy the energy principle because the change in the total amount of energy is zero throughout the oscillation. There are no outside forces working on our system of the mass, the Earth, and the spring, meaning that the energy in the system will be conserved. As you can see in the graph below, the orange line, which indicates change in total energy, is zero. If I had perhaps decided to use the x position values in order to calculate the period of the oscillation, the period would instead be 1.66 seconds instead of 1.5195 seconds. The reason why we use the y values is because the spring is in the y direction rather than the x direction. Using 1.66 seconds instead of 1.5195 seconds would make our spring constant smaller and therefore a smaller resting length of the spring. In the long run, this would lead to a greater calculated spring force, which would create large discrepancies between the model and the experiment graphs. Thank you.